Hi, I'm Dr. Tom Calabrese, and welcome to this week's installment of Insights into Computer Science. This week, we'll be talking about control logic, engine design, and finite state machines. Up until now, most of what we've been doing is relatively simple and straightforward. Calculating a factorial or the tax and tip on a restaurant tab, or maybe something to convert Fahrenheit to Celsius and Celsius to Fahrenheit, even simple calculators and databases. These programs are all similar at their core in that they request data from the user or other sources, do some calculation, print the result, and perhaps go around again. Even our game of four-dimensional tic-tac-toe, as described in an earlier video with its elegant memory constructs, still follow a similar control design to these other programs. In computer science, there's often a need to have a more advanced form of control logic known as the engine. Formally, an engine is a continuation-based construct that provides timed preemption. Whoa, that's a mouthful. But what is it and why is it so important? Well, you probably don't realize it, but you use engines every day and control logic all the time. Driving assist software that runs in your car, or personal assistant software, video games that you play, and so on. In computer science, the use of an engine is an important design construct. Engines are at the heart of most programs that fall into the classifications of modeling, simulation, and gaming. All of these have a couple of things in common. Most importantly, each of these requires that the designer have a timing mechanism built into the program that allows the program to keep events that occur during the program execution on some kind of a timeline, real or imaginary. So for example, if I were building a traffic simulation program for the downtown area of some city, I would need an engine that would do things like add or introduce and delete cars, trucks, motorcycles, etc. at the main entrances and exits of that downtown city map. Control the changing of streetlights, empty parking garages during the rush hour period. Vary the vehicle insertion rate depending on the time of day, stuff like that. What's important to note about these things, we call them events. They happen all day long. And based on the data we use to support our simulation, we can continually change the rate of these events based on the simulation timeline or a clock. In this case, we could use the actual clock based on the computer's understanding of time of day, or we could create a simulated clock based on the length of time it would take to make one iteration of the control loop of our program, a sort of imaginary clock, if you will. Many of you play video games, I'm sure, and you play these games in real time. In those instances, you want your game engine to update the events happening in your gaming world, or the scenes, in real time. Interestingly enough, computers have no real sense of time. They are basically stupid. They do what you tell them to do. So even real time only has a narrowly defined meaning to a computer, another tick of the clock. If we want a number of things to happen in 1 second, we need to design our gaming engine in such a way to be sure that the timing requirements of the game can be accomplished as planned. Now here's the kicker. 1 second of computer time can be used to accommodate an absolute ton of human events. Let's take, for example, the beating of a human heart. If an average person's heart beats at a rate of 72 beats per minute and 60 minutes per hour, times 24 hours a day, times 365 days a year, times 85 years, then the heart would beat a total of 3,216,672,000 times during that person's lifetime. Now, let's say we write a program in a simple loop that beats a computer heart that same number of times. Further, let's assume that we do this in, say, 5 instructions. That being true, we would need 16,083,360,000 computer instructions to execute to complete that simulation. Now, if we were to use a 3.2 gigahertz single processor to do that computation, that would mean our computer could execute 3,200,000,000 instructions per second. So if we divide 16,083,360,000 by 3,200,000,000, this would tell us that we can simulate 85 years worth of heartbeats in 5.02605 seconds, or roughly 16.91 years of heartbeats per second. This tells us that our engine needs to actually slow things down to make them happen in real time, or to make things in real life, like the traffic in our downtown area, seem real. Of course, it might be useful to be able to speed things up inside the computer engine so that we can simulate the effects of, say, a year's worth of construction on commute times of travelers that pass through the downtown area averaged out for that year, considering other coincident events such as weather, sporting events, parades, and so on during the whole year. Okay, so back to our definition of an engine as a continuation-based construct that provides timed preemption. A continuation-based construct is a data structure, or what computer scientists call a context block. The context block is used to track the current state of a program as it executes based on the events that take place during the simulation, let's say. These context blocks are useful in 2 important ways. First, they provide inter-process communication. And second, they allow us to pass state and scene information forward in the engine's timing loop. This is where finite state diagrams come in. A finite state diagram is a pictorial representation of the operation of a program. Let's consider a simple coin-operated soda machine. A soda machine is an example of a real-time system. In this case, we want to represent our soda machine as having 5 different states: refrigerating, counting, selecting, dispensing, and making change. Our machine starts out in the refrigerating state as a matter of course. At some point, a customer puts a coin in the machine, and that's when the fun starts. In this case, we will define 8 events labeled A through H. These events are the initial coin drop, the coin drop and a count greater than or equal to the price, the push selection button, the soda drop and count equals price, the soda drop and count is greater than price, the drop change event, the pull lever event for a return, and the drop change and count less than price event. Now, our finite state machine diagram traces out only the normal operation of the machine. So, the machine starts out refrigerating. Then someone drops the first coin, which causes the machine to start the counting process. Next, the customer keeps dropping coins until the price is reached. That activates the selection process and allows the machine to take input from the selection buttons. At this point, the customer presses a button to select a soda. The machine moves to the dispensing state. In this state, the machine first checks to see if the count is equal to or greater than the price. If it's greater than the price, the machine drops the soda, then enters the making change state. In this state, the machine calculates the amount of change required, counts the coins, drops the change, and returns to the refrigerate state. Notice that this represents only the normal operation of the machine. In order to consider all the possibilities of events and state interactions, we need to look at a transition matrix. The matrix of this type shows all the states on one side and the events across the top. The grid of boxes represents the actions based on the event state pairings. By doing this, we check all the possible pairings and then decide what action, if any, that you want to take for that particular pair. Now, our engine considers this information based on consecutive timed passes through the control loop. In the case of the soda machine, we would create a structure to pass the information about state of the machine forward in time or to the next iteration of the loop. In that next iteration of the loop, events are processed, actions are taken, including the updating of the state variable, the context is restored or updated, and the engine moves through the program forward in time in a similarly controlled way. Okay, so let's go back one more time to the definition of an engine as a continuation-based construct, got that part, that provides timed preemption. Time preemption has to do with the transfer of control between competing computer resources. In this case, we may have more than one active process running simultaneously. In many real-time designs, the engine manages consumption of computer resources by rival or competing processes. Let's take, for example, a factory or processing plant that may have a variety of sensors, each running its own process called an agent. That reports back to some centrally based server running the monitoring engine. As those agents report back to the server, the engine decides which state event pairing combinations require attention in the given time frame and then has the ability to prioritize those actions that need to be taken and ordering them all while maintaining this timeline. Sometimes the engine needs to pass information from one agent to another or between two different processes. To do this, we create the context or control block. This piece of memory is shared between two processes, or more precisely, between the active memory of the engine and that of the agents in this particular case. Inside the control block, we allow one process to signal another process to take or not take an action through the use of what are known as flags. Flags are bits that are set to 0 or 1, indicating basically by their position which action or function is available. In the control block, we can maintain counters, clocks, input-output buffers, a state variable, or something called a semaphore or lock. These locks, while they're similar to flags, they prevent code from entering what is known as the protected area. For example, if we were designing an internet router, we would realize pretty quickly that the router has two mutually exclusive functions. The first is the forward data function based on the routing table, and the second is the updating and maintenance of that table. It should be obvious to you as to why they are mutually exclusive. I mean, you can't forward things based on a table that's constantly changing. Remember the early days of GPS driving assistance? You're driving along and then there's an update and the thing says, turn now, and you're going 40 miles an hour and you're 10 feet from the turn? Well, the same is true here, except that the router software engineers realized not to do that. They made data forwarding and router table maintenance or routing updates mutually exclusive. And to do that, they used a software lock or a semaphore. When the semaphore has one value, the data forwarding code operates and the routing update code waits. On successive passes through the router's engine, rechecks are made and the value of the semaphore could have changed. If it does change, then this will stop data forwarding and enable routing updates. This continues with respect to time over and over and over again, and it's really efficient. I mean, routers forward data 99.999% of the time and only really do routing updates very occasionally. So why use something like a round robin system where you'd waste a lot of computing cycles? Instead, using the semaphore allows the system to spend its cycles doing its main job, which is most of the time forwarding data. You might think this concept is really tough to implement. Based on your current understanding of coding, that seems reasonable, but if you take our pretend example above and this code, you can see that the context block is easily constructed using a struct command in C, and the engine itself would be based on a simple while loop, containing a variety of function calls and other simple logic. The designer controls the time value of one loop pass based on the number of actions that are required at each interval and the state event pairing of the finite state machine. For example, in the simulation of traffic in the downtown area, the computer scientists would work with city planners, engineers, weather people, the Department of Works, to understand all of the variables that affect traffic in this particular model. Then a team would go out and collect real data about traffic flow in the city by actually counting cars in various places all day long. They measure the duration of light changes at intersections and notice the time and duration of events that are significant, like how long does it take to empty a parking garage after a concert or a show? Based on all that data, the computer scientists can calculate the representation of time per loop pass and the actions that need to be checked and processed during that pass. Then the simulation can run and time adjustments can be made to allow the simulation to run in real time, slow the computer down, or just allow it to run at the rate of the computer to enable researchers to, say, conduct an analysis of construction and delay times in the system. I have always found the concepts of engine design, finite state machines, and generally control logic to be very interesting. And I spent a good portion of my career working on these kinds of real-time projects. If you are following this series as you take courses in computer science, then you'll see that as you learn more advanced programming techniques like structures, type def, mallocs, classes, and class control in object-oriented languages, callocs, threading, and semaphores, designing real-time systems, gaming engines, models, and simulations will be pretty straightforward and a lot of fun to do. So until next time,